Good morning. Today we're going to be working with the list structure we're using for our CS2420 class on data structures and algorithms. And we have right here our UML diagram we're going to be starting off with. As you can see right here, we have a list of type. And so that indicates that we're going to be using it, again, since we're using C++, we're using the templated type about this. So it can be worked with any type of data that we want to store inside C++. Because the angle brackets type and the template class type key phrase that we're using in C++ makes it so I don't have to make a list of car, a list of rubber ducky, a list of int, and a separate code for each of those different files. Instead, we can simply have a single file, in this case right here, list.hpp for our template header file, the reason to do all the work for this. Now, because we're using C++, we're going to use what's called an abstract base class to implement the structure for this. It's similar to what we see inside a Java interface, where it's a collection of unimplemented method headers, but we'll go over that in just a bit. Here we have the actual design that we're working with, so we can see what's going on inside the structure of our class before we even get to actual code itself. And so in our data member section, you can see we have a single data member that all lists are going to have, and that's the size. We have some methods we're going to be using in all of our list implementations, and so we have them grouped in two different sections right here. And because this is an abstract base class, as you can see going down this lovely list right here, every single one of the methods we're working with are all public because they are all going to be used by all of the subclasses. These are things that have to be external for all our components, and since it's an abstract base class, the general rule is that if it's a base class, it's going to be public because you're going to be using it externally. Maybe possibly protected if it's going to be a helper method that all subclasses might have, but for what we're working with right now in list, everything inside this is all going to be in the publicly available field. We'll see some abstract base class implementation where we have some protected methods to work with later, but for right now, we just have public for this. And so we have right here, we have an add that takes a type, and again, that matches that template type right here we're working with, because whatever we put inside this, we can decide as an add for that, and it's a type-based list. It's using the angle brackets, so we know exactly what's going to be stored inside our data structure itself. We also have an add-index method, and again, I'm using a method naming convention right here where we can see that we are explicitly using add an index. We know that when we see the actual method name itself, we know what we're doing with the method, and its first parameter is an index, its second parameter is the type, and that also is a void type method. We have a remove method that takes an int as a parameter, so we can remove a single value from the list. And so we have all of our list objects will have a remove that takes an int parameter to work with. We also have our public method get from index, and that's going to be how we can actually retrieve a value without removing it from our data set. And so those are our manipulation methods we have to actually work with the actual structure of the list class. We then have some getters that all of our list subclasses are going to need, possibly for some purpose or another. We have get size, get front, and get end. And as you can see, get size is a const, where it refers to the int, the actual size. It's a getter, really hashtag basic, we have to worry about that. And then get front and get end refer to the actual pointers we're working with inside our structure. And because of what we're doing for the subclasses of list, I chose not to implement the front and end as actual as actual data types. Rather, we just have a front and end, so we have that as a method so we can actually grab those values as needed internally, and we'll talk about that in just a bit. So here's our actual UML diagram where we're going to work with that. Let's take a look at the actual code and what we're going for with that. So we're going to switch over here to the list.hpp. Again, we're using a header file on this because of the fact that when we are using a template class type, as you see right here in line 15, that template class type, what that does is it actually says that this will work with any single data type that we want to possibly store. And so we have that size, plus or minus 2 billion, way more than I have to worry about for the idea of using a structure with that we can have an int as a type. If we're actually working using this for more than simply just a testing purposes in class, we'd look at actually using a long for that data type. But for purposes of this, we're using 117,000 entries we're going to be measuring this against, and so int totally fits within the realm of what we're going to be storing for that. And makes a lot of sense. In our public section, we have the structural methods and the helper methods that go along with this as the class. And what you can see right here is the way we work with an abstract base class, there's not an abstract keyword like we see in Java. So it's just regular class lists that we see just like defining a class. And of course, template class type to assign that. But we have, in order to make something to be abstract, what we have is the virtual equals 0 sequence. By saying virtual allows it to be overridden. And by assigning the equals 0 after the actual prototype for the method, that says that it's completely unimplemented. There's no attachment to this. And this goes back to the fact that C++ really is just a superset of C. And that sequence right there is basically saying this is all undefined with the default minimal possible value of 0 that we have in C. And so that virtual keyword is saying it's going to be overridden at subclasses, and equals 0 means if we want to have it be a non-abstract class, we have to actually give it some information for that, is what we're going for that. And so we have virtual void add, taking a parameter type item, equals 0, and that equals 0 is going to be replicated on all these lovely values all the way down that we're working for on that. And so add index takes an index parameter as well as a type item. remove takes an int index parameter, get from index takes an index parameter, and get size, get front, and get end, and their associated return types of int, LinearNode type pointer, and LinearNode type pointer to retrieve those values. And so all of our different structures that we're going to be using for our linear data structures, you can see over here on the left, all those are going to use this as that base framework. Now you can also see right here that inside my list HPP, I have my hashtag if and def hashtag define that we use to actually give the preprocessor information to say, oh, here's what I need to define this class so I can, when I'm building this, it's going through the linking phase of the compile and build structure. That's where it's going to get those definitions. But we have right after that, we have two hash includes. The first hash include is assert.h. I'm explicitly using the assert.h right here at the abstract base class level so that all the subclasses have that already pre-linked inside that, because when we're using the hashtag include, we want to have it available. So the first class that's going to need it, in this case, the abstract base class, when it's at the very heart of all the classes, already has that include right there. So I only have to include it once, and it's already there inside my structure, my project. So I don't have to worry about anything else like there. Then I have my hashtag include nodes/LinearNode.hpp. And so what that's doing is that's telling me that when I build my linked list, I have a reference right here immediately to go with all my linear nodes, because I have right here LinearNode of type pointer that's going to be attached to that for my lines 29 and 30 where I actually pass those in. That dot allows me to go up to the folder above it. And as you can see right here, list, I'm going to go up to the level that I'm at beforehand, which is the same level right here of linear. I want to go up one more level to structures. And then now I can go down into my nodes folder. From my nodes folder, I'm going to go inside that. I'm going to grab the information for LinearNode.hpp. So I can actually link into that. And so this allows me to build my code so I can immediately have a reference to LinearNode at the heart of what I'm working with. And so we'll be using this for all of my structures. And again, because this is an abstract base class, I can't actually make a list. This code right here is designed so I have a framework so I can use it in all my subclasses. And we're going to see how that's actually put together. If I take a look at my list structure right here, and so my list of type, I'm using this right here. I have my reference to go along with this. And so again, I have that same UML diagram we were looking at earlier. And I'm using the composition relationship here. And so my list of type is composed of linear nodes. Now I explicitly say it's composed of 0 because this is an abstract class. And so my subclasses will actually have 0 to n of those, where 0 by default, and then n as the actual list itself grows for it. But because it's an abstract base class, I still have that composition relationship. Even though none of them are actually in here, it would be composed of that type. And so we can see that we have a relationship between the actual data structure and the data component we're using to hold that, which is, again, a subclass of the node type. And so we have that relationship we're building for that. As we continue on and look at our other data structures, we see that relationship actually build and grow for that. And so we'll continue on with this. But so we have right here, again, our link, our list data structure, which is an abstract base class. It's going to form the framework for all of our linear data structures we're working with, as you can see right here, of linked list, queue, stack, and circular list. So we can actually have that ready to go. And that's what we're going to be building for on this. And so we continue on from that to actually build our data structures and go from there. And so that's what we're working with as the structure continues. And thanks. Have a good day.